Hello, I'm Takashi. What I'm going to present is about a novel off-policy meta-reinforcement learning method based on future embedding spaces. I will begin with brief introduction of deep reinforcement learning and meta-reinforcement learning. As you know, deep RL has shown superhuman performances in several domains, such as computer games and board games. But it is also known that DeepRL is not sample efficient. MetaRL addresses this problem by applying knowledge obtained in past tasks, while conventional DeepRL does not. However, most MetaRL methods are on-policy. In general, on-policy methods are more sample efficient because it can reuse data collected by all policies. To improve sample efficiency, we propose a novel off-policy meta-RL method. Meta-RL consists of two phases, meta-training and meta-testing. In meta-training, the agent runs in tasks which are similar to a task to be solved in meta-testing, to extract useful knowledge for learning in meta-testing. In meta-testing, the agent runs in the task to be solved, and also its performance is evaluated. The objective of meta-RL is improving sample efficiency in both phases, that is, reducing the amount of data needed in both phases to achieve a certain level of performance in meta-testing. I give an overview of our method. Our method considers an embedding space for task features and runs relationship between task features and the policy beforehand. More concretely, in meta-training, it runs mapping between task data to a distribution over the embedding space and the distribution to a good policy. In meta-testing, our method uses the round relationship and infers what a good policy is. Thanks to the inference based on the round relationship, policy can be improved with a small amount of data if the embedding space is well trained. In case the embedding is not well trained, our method also updates the parameter of neural networks after the inference. That's an overview of our method. This is an architecture of our method. Our method consists of two parts, networks for learning embedding and networks for learning policy. Our method runs embedding like conditional variational encoder. More specifically, there are an encoder and decoders. The encoder gets data and output parameters of and distribution over the embedding space. The decoder gets sample variable from the distribution and reconstruct data. They are trained to accurately reconstruct data. The round distribution is used as a part of input of policy, Q function, and V function. They are trained like soft-actor critic. All are trained in an off-policy manner. These are experimental results running curves in meta-testing. We compared our method and the existing ones. In the experiments, the number of time steps in meta-training of each method is the same. The results showed that the proposed method were more sample efficient than existing ones.